everyone and welcome to the channel Binpipe School. You are with Bijayalakshmi and today I am going to derive the second equation of motion using graphical method. If you remember, I have posted a video on derivation of first equation of motion by graphical method, and come on, let's derive the second equation of motion. Now in the second equation of motion we will also begin with a graph. And this is a velocity time graph. So velocity we will keep it in y-axis, that is in meters per second, and time will be in x-axis, that is in seconds. Okay, and this origin, let's name it as O. Now suppose a body starts its motion from initial velocity u and attains a final velocity v at t time taken. Suppose it takes a time t. Okay, and let's name it as q, the point where it reaches the final velocity, and if we drop a perpendicular from the initial velocity point here on this line QS and name it as RP. Okay. Now here what we get? We get a area, isn't it? Now this area that we see resembles the area of a quadrilateral. Can you name the quadrilateral? I hope you have guessed right. It is a trapezium, right? Now this area that it covers is the distance covered by the body. Actually the acceleration covered the acceleration graph, we can say, of velocity time graph defines the distance of the body. This area defines the distance covered by the body. So that is why we take the help of this area of trapezium and then we derive the graphical method. This is the hint, you can say. So these are the letters or literals or variables that we have assumed. Now as we know the area of a trapezium as, you can write here, area of trapezium is equal to half into sum of parallel sides this is a parallel symbol, short form, into distance between the parallel sides. Now which are the parallel sides? These two are parallel sides. And what is the distance? This is the distance, isn't it? The perpendicular. Sum of the parallel side and distance between the parallel side. Or we can also write as height. Sum of the parallel side into height. So area of the trapezium, instead of area, we can write as S. Since I told you the area defines the distance covered by the body, into half of sum of the parallel sides. Sum of parallel side is, which is the parallel side? OP plus QS into distance between the parallel side, that is OS. So we write half into, instead of OP we can write as U plus, instead of QS we can write as V into OS, that is we can write as T. So half into U plus. Now instead of V, can't we write or can't we use the first equation of motion, that is V is equal to U plus AT. Now instead of V, value of V, we can put U plus AT here. Because in second equation of motion there is no final velocity used. Okay, so instead of that we use u plus at and multiply t as usual. So what we get after multiplying half and t to every equations, finally what we get is 2ut by 2 plus at square by 2, s is equal to 2 gets divided, so we get ut plus half at square. So this is what is called as the second equation of motion, and this is how we can derive using the graph, and especially the trapezium is the one that helps us to give the formula. The area of the trapezium helps us to derive the formula s is equal to ut plus half at square. Now using this second equation of motion, we can get any one of the parameters if the other three parameters are known, that is distance, initial velocity, time and acceleration. Stay connected for the next video on derivation of the third equation of motion. Do subscribe my channel if you haven't yet. Thank you for joining.